Thank you. Thanks very much. It's a great pleasure to be back at the Royal Institution and talk about my favorite subject on a Saturday night. There's nothing better than that, actually, and I'm very happy that there are a few like-minded people who have nothing better to do, probably, than listen to this. This is a title of one of my books, but actually I want to go beyond that, and I want to tell you about something new. And the summary of what I want to say really is that I think the right way to understand the foundations of physics. So, as you know, physics really tells us about what the universe is made of. And traditionally, you know, if you open the Oxford Dictionary or something like that, it will say it's a subject that studies interactions between energy and matter. And I think what we've realized through quantum mechanics is that actually it's probably better to think of it in terms of information, but it's a very peculiar kind of information, and that's exactly what I want to tell you about. And I'm summarizing here that it's a kind of interplay between quantum waves and what it means to be a quantum wave is something I want to explain at the beginning. And why it matters to understand it this way will come in the second part of the talk, because I think that this informs us how to look for the next theory of physics. As most of you will know, we've had about 100 years of general relativity and quantum mechanics, just about proven in every experiment so far. But I think we are really at the verge of being able to explore this new territory. And it's because of the progress of the experimental side of quantum technologies. That's the interesting thing there. But let me go into it. So when I talk about information, I really mean it in a very specific way. Information is possibly the most abused concept when you read about it. And people talk about it frequently in a very careless way. And I think language, of course, as we know in science, can be very misleading, which is why we like to define these things. And I just want to say that the information that I have in mind, and I think all of my colleagues in this field, would go back to Shannon. So what Shannon said is, if you want to understand the information content of an event, if something happens and you want to attribute information to that, then all you need, and that's the interesting thing, all you need is the probability for that event. And once you have the probability, and you have a couple of very simple requirements what the information ought to do, then Shannon said you are left with only one way of quantifying this information. And it's basically log, the minus log of this probability. Now, let me just briefly comment on this. Minus simply means that it's inversely proportional. If something is more likely to happen, it carries less information. So something really surprising, you know, like having 30 degrees temperature tomorrow in London is a probably very low probability event, and that would carry a lot of information according to this logic. The log, and that's the interesting thing, the log is there because you want independent events. So the events that really in no way influence one another. You want the information to add up for these events. So let's say the probability for me to walk out right now and stop the lecture, and the event that in Singapore we have a tropical storm. Now they're presumably independent events. I don't think they influence one another. And what Shannon would have then said, take the probability for one, take the probability for the other one, multiply them and take the log, and that's going to give you the sum of these two informations. And that's it. It's a unique measure, very interestingly. So all you need is a probability. And you can already now see what I'm probably going to do. I'm going to argue that effectively in classical physics, in Newtonian physics, which is fully deterministic, anything non-quantum is basically what we call classical, not even just Newtonian. electrodynamics of Maxwell's general relativity of Einstein is all classical in this sense. Probability is only effectively there because we lack information. If we didn't lack information, probability would not exist at all. If we really could know all the states of all the particles in the universe at the beginning, and we could calculate using Newton's laws, we could predict exactly deterministically what's going to happen at any instant in time. So either something happens 100% or it never happens, zero probability. So probability doesn't have that fundamental meaning in classical physics. However, in quantum information, it's inescapable. And that goes to the heart of quantum mechanics, actually. That's what I want to talk about now. The reason, of course, you would have heard about Heisenberg's uncertainty principle, and that's exactly at the core of that. But I want to phrase this in terms of information. And that's where it gets interesting. So you can use one property of your system, let's say the position of your particle, as an information medium. And it's a perfectly legitimate medium. If it's located here, that could be a logical 0. If it's located here, that's a logical 1, and so on. You can get as many bits of information as you like in principle. However, what quantum mechanics says is that the speed of this particle is another possible information medium, but if you put them together, they cannot constitute an information medium. And that's very interesting. And the reason for that is that once you know perfectly the position, one of them, let's say, of your particle, you have no idea what the speed of the particle is. And probability, therefore, and people call this under various other, some people may object to the fact that I'm calling this a probability, but there is some intrinsic uncertainty, indeterministic, whichever word you want to choose here. If you know one of them, you really cannot know with certainty all of these other properties. So quantum mechanics is weird. It's got infinitely many classical information media, but when you put them together, they transcend that. Some people might call it super information. It gives you really superpowers compared to classical mechanics. And that's actually the heart of this. That's at the heart of all our quantum technologies as well. So let me tell you what the fundamental picture of the universe according to this really is, the current state. And then I will try to tell you how I think this will guide us as to what it is that we ought to be testing. So even though currently you have many interpretations of quantum mechanics, and I think every researcher will be as confident as I am here in front of you, and they will tell you my view is the right view of quantum mechanics. At present, we frequently can't tell them apart experimentally. However, what they do influence is the experiments that you want to perform and the experiments you are planning. That's where it's very important. If you think quantum mechanics will collapse at some point, and we're going to go back to classical physics, this is going to give you it's a very different philosophy that's going to influence directly what it is that you'll be looking for out there. My claim will be the exact opposite, actually, that it's perfectly consistent that everything is quantum. We don't know if this will continue like this, but for now, we have no reason to expect that quantum mechanics will fail. And that's what's interesting, I think. Okay, it goes back, maybe the best way to explain this kind of complementarity. Niels Bohr called this complementarity. Sometimes it's called duality, dual nature of quantum information. At the beginning, there was a famous paradox that was discussed a lot in the early quantum meetings. And I think it followed Schrödinger's discovery of his famous equation. And Schrödinger's equation, even though it's written for particles, it's actually a wave equation. So Schrödinger somehow claimed, following de Broglie and a few other people, in fact, that particles ought to behave like waves. It's not just waves that are made up of particles, like light is made up of photons, but it's the other way around as well. And then there was a problem. And the problem was this experiment involving alpha particles are like nuclei of helium, so they have like 2 protons and 2 neutrons, and they get emitted in some nuclear reactions. And when you look at them, they come out in straight tracks. They really do behave like particles. It's almost like what Newton would have modeled with his own classical mechanics. And yet, at that time, people already suspected that these objects are quantum mechanical. And if you want to understand them, you really have to use the wave equation of Schrödinger. So there was an immediate problem there, saying, wait a second, I mean, if you claim that they are waves, why do they behave like particles? This is this famous wave. And you can think of waves and particles just like the position and momentum. 2 classical media for information, but put together, they transcend classical information. They become quantum information. I'll get to that now. So the question, the mystery at the beginning, this is late 20s, almost 100 years ago. The mystery was, why do they behave like particles? Why do they actually go in straight lines? Shouldn't we get something like this? Shouldn't we have an observation where a wave, you know, they literally come out here and the wave spreads out isotropically equally in all directions? Isn't that what the wave equation, every wave equation would give us something like this? And that's interesting, actually. And the answer came in a sequence of papers. One was by Heisenberg. That doesn't probably surprise you, the guy who started the whole quantum mechanics. Then there was Darwin. Probably Darwin's writing is my favorite. If you go back to his 1930 book, popular book on quantum mechanics, I think it's still the best popular book ever written on the topic. This is, by the way, not the Charles Darwin. It wouldn't surprise you, it's the grandson, also called Charles Darwin, very famous physicist. And finally, I think the paper that we all quote ultimately, the person who did, another Nobel laureate, person who did the most extensive analysis was Mott. So Mott explained how to use Schrödinger's equation to get the tracks that look like classical particles out of a wave equation. And this goes to the heart of quantum mechanics. This is what we all argue about at every conference. How can it be like that? You know, that's kind of one of those things, as Feynman would put it. And the point is the following. All of these people said something like this. The particle initially, the alpha particle, goes in all directions simultaneously. That really is the case. But then what happens inside this cloud chamber, the way you detect them is that you have a gas of molecules, and when the alpha particle hits the first molecule, it ionizes it, it excites it. This energy attracts a vapor, and you can see a tiny cloud. And the alpha track is a sequence. It's a discretized thing. Maybe you can't see that on this image very well, but it's actually a discretized sequence of clouds. A bit like an airplane, actually. It's exactly what the airplane does when you see the track in the sky. That's kind of the mechanism for how this happens. I think these cloud chambers resulted themselves in 6 Nobel Prizes. You can probably Google it, find the YouTube video, and you can use your kitchen utensils to make it in 10 minutes now. Anyone can detect these kind of things at home. Now, the interesting thing is that as soon as you get a collision here, what Mott calculates, and all of these guys, is that the probability to get the next collision along the same line is almost 100%. And that's interesting. So it's a bit like a measurement record. Yes, the alpha particle goes in all directions at the same time, but actually the reason why you see a straight line is because it's a sequence of measurements that you see. And every time you do an experiment, you see a different sequence of measurements, which is why you see many of these alpha particle tracks. That's the logic. And now comes the punchline. And I think all of these guys have asked the same question, actually. The punchline is, what happens if you treat the gas quantum mechanically? What if everything here is quantum mechanical? And the answer is, and Mott gives this answer as well. And in fact, lots of other people give this answer, and I strongly support this view of quantum mechanics, is in fact that all of these tracks exist at the same time. All of the experiments we've done so far, and I'll show you how far we can go and we intend to go, tell us that actually in one branch you will have this straight line, but in another branch simultaneously in a quantum superposition you will have another branch and all of them at the same time. The word you will hear sometimes is many worlds, and it goes to a guy called Everett. But all of these people were many worlds 20 years, 30 years before Everett, actually. And that's the interesting thing about the whole enterprise. So what this says is that it's perfectly consistent to think of everything as quantum mechanical. It doesn't prove that everything is quantum mechanical. We have to test this at larger and larger scales. But it says, logically, there isn't any contradiction. This is probably contrary to what you'll be reading about in various things. And I'm going to contradict many things you might have seen in the popular press. I think they're just wrong. And they will be proven, hopefully, more and more wrong through our experiments. Here is exactly what Heisenberg did. I'm just going to give you another snippet. I don't want to write too many equations, obviously, that's not the point here. But Heisenberg had an ingenious way of reproducing this. It's ingenious, and I think it's a shame that we never teach it like this to our students. We always follow Schrödinger, never Heisenberg. And actually, he was the guy who I think had the right view of what was going on. I'll get to that as well. So what Heisenberg said is this. Heisenberg said, the problem with Newton's laws and all of classical physics are not the laws themselves. The laws are okay. And this could be a shock to you, because that's not what you hear. The dynamics is completely okay. You don't need to change it as far as quantum is concerned. May have to change relativistically, but it's a different reason. So what he says is, I'm going to take Newton's equation. This is the simplest thing you can get. It's a particle, position of a particle at time t, given the position at time 0, speed of the particle and time. Everyone knows this equation. This is a free particle, no force is acting on this particle. And here is the genius idea. Heisenberg says, Newton thinks that these things are numbers. Position is a number, 5 meters away from whatever is your reference. Speed is a number, 10 meters per second, or whatever the speed is. But Heisenberg says no. They are new entities. They turn out to be quantum numbers. Dirac called them ultimately Q numbers. And he said the mistake in classical mechanics is not the law, it's that the entities are not your classical information. They are actually quantum information. They are these Q numbers. And it's really an ingenious idea. And if you treat these not as ordinary numbers, and what's the thing that they fail? They fail to commute. When you multiply two ordinary numbers, it doesn't matter which order you multiply them in. But when you multiply two Q numbers, two matrices, you get a different result, whether you first multiply position and then the velocity, if you like, or vice versa. That was the genius. So you don't need to discard classical physics. It's completely okay. What's not okay is that fundamental entities are not real numbers. They're Q numbers. And that's the end of it. That's the beauty of that. You know, sometimes you will read, quantum mechanics says there's no reality. This is another nonsense way of popularizing anything in quantum mechanics. Quantum mechanics says there is a reality. Obviously, there is. None of us would be doing physics, I think, if there wasn't any reality. But it's a Q-based reality on these quantum numbers, not on classical numbers. So Heisenberg says, when you have this alpha particle coming out, it's going to spread a little bit like a wave. But if your gas around this particle is very dense, it's very quickly going to collide with the first molecule of the gas, and that's going to localize it. You will know exactly where this is. Then it's going to continue to spread a little bit quantum mechanically like a wave. It's going to hit another molecule, and that's going to localize it. And effectively, a sequence of things like this recovers the straight line of Newton. But in quantum mechanics, there are no straight lines. Even Newton said straight lines don't come from God, but they are drawn by freely moving particles. No, they are not. They're only approximately drawn. That's what we found out through quantum mechanics. So the key idea is you don't need to change the laws. You're changing the fundamental underlying elements of reality. They are Q numbers. They are not real numbers. They obey different algebra, if you like. And it's an easy algebra. It's not difficult to learn this at all, actually. So I mentioned Everett already. And I think the beauty of this picture, in fact, Schrödinger, maybe a year or two before he died, gave a set of lectures in Dublin, which were published much, much later, which basically say more or less the same thing as Everett. I think Everett wasn't aware of that. But Schrödinger really, if the title of the originator of the many worlds interpretation should go to anyone, it should be Schrödinger. And the thing that he really liked is that you don't need, first of all, you don't need anything special about observers. Notice that what I was talking about is the alpha particle being observed by another particle, by a molecule. It doesn't have to be a conscious entity. It doesn't have to be a living system. Anything suffices. Anything that can couple to your system suffices. So it's another thing that I dislike. I'm, by the way, writing another book, and I will tell you about it as well a little bit. And I'm venting my spleen on the. I really don't like reading certain things about what quantum mechanics really tells us about the world. One thing you will hear is that we create our reality. We don't really create our reality. I think it's more the other way around, if anything, and I will tell you a little bit about that as well. There are no collapses. That's what Schrödinger didn't like collapses at all. He said, I would have never become a quantum physicist if I knew that this is about collapsing of anything, instantaneously happening here and there. So basically, this avoids the distinction between observers observed. Observers are nothing special as far as this is concerned. It basically avoids all discontinuities. There is no spooky action at the distance either. And that's going to be probably surprising to you, because we always say spooky action, entanglement. There isn't anything spooky. Nothing travels faster than the speed of light in quantum mechanics. It cannot. And things like that. So basically, this is more or less the summary of this. The beauty of taking everything as being quantum mechanical. And it's really interesting. So not only does this not generate any problems, it in fact gives you a more consistent picture of reality. So you should think really of the whole universe in this way. And so this is my slide on entanglement. Again, I don't really want to go through this logic too much, and there was a Nobel Prize, and I think lots of you have been reading about these things. So one announcement that I wanted to argue against was this, that these experiments prove that there is no reality. They don't prove that there is no reality. They prove that the reality is not based on what we call real numbers, but it's based on these Q numbers. Dirac called them C numbers, classical numbers, and Q numbers for quantum numbers. And once you do that, you don't need to change anything in classical physics, nothing else. That's the amazing thing about it. So what this really shows is that you can never, if you have two systems that are entangled, people like to say, I measure one, and suddenly I collapse. I obtain information about something that's far away, and I do that instantaneously. And if you stick to Q numbers, that's not what happens at all. That only happens if you stick to real numbers. If you really say, but I want to know whether this system is spin up or spin down before I did any measurements. If you insist on preserving classical reality, you're going to have to assume that something indeed travels faster than the speed of light. That's the point here. And the whole point of quantum mechanics is we can preserve locality. Everything is nice and local, exactly as Faraday would have done it in his lectures at the beginning of this institution. So, you know, he would be moving a magnet, he would be generating a current, and this would turn the needle on the magnet at a distance. But there was a perfectly local and causal explanation of how this works. And I think it's exactly the same in quantum mechanics. The weird thing are the Q numbers, that you have all of these informations packed together in this funny way. And I think so that's the key to that. And in fact, this is just maybe one mathematical representation of entangled, many entangled systems. What I want to claim now is that the right way of understanding this is that even the classical physics, as we call it, exists because of quantum mechanics. So this is another thing that we don't teach this way, even in our physics courses, is basically the fact that logically the right way to teach this is to start with quantum mechanics, which is a more fundamental theory, and then argue that classical physics is a special case of that. So actually the reason why in this macroscopic world we largely, to a good degree of accuracy, obey Newton's laws is because there is a lot of entanglement. It's because it's really quantum mechanical that somehow it looks classical to us in the macroscopic domain. That's really interesting as well. So even classical physics owes it to these kind of Q numbers of quantum mechanics. And so this is one of those topological entities where all of these rubber bands are inseparable. They're entangled to one another. However, if you remove one of them, then all of these fall apart. They're the Borromean rings, or whatever they are called in topology. And so being highly entangled is very much like that, mathematically speaking, that it looks quantum mechanical at the highest level. However, if you look at subsets of reality, they conform to classical physics pretty much. So actually the reason why we find it difficult to do quantum experiments with larger and larger systems is because all of the other entanglements with the rest of the universe prevent us from seeing the quantumness in the object itself. It's very interesting. It's not that something in nature is trying to make things classical, it's that this happens naturally within quantum mechanics. And I think that's very interesting. Here is the advert, okay? But what I want to briefly summarize is exactly why this is interesting. So where am I going with this? I want to ask, what is the next frontier for us? What is the first question that's accessible to us that we don't know the answer to, and that this logic would lead us to actually probe? And the interesting thing, I already alluded to the fact that if you have two quantum particles, if you start two classical particles in the same direction, they're going to move in parallel. If there are no forces acting on them, they're going to obey the Euclid fifth postulate, whatever it's called in Euclidean geometry. Two parallel lines are never going to meet. However, in quantum mechanics, because they spread each of them, there's actually a probability that if you put a detector here, you will get two clicks. You will get two particles here. So this already tells you that there is something interesting about geometry. The quantum, incidentally, that's how Dirac arrived at quantum mechanics. He understood Q numbers in classical geometry, that they have a big effect. He attended lectures on using matrices instead of real numbers in classical geometry, and that gave him an idea how to basically apply that to quantum mechanics. So here is the interesting thing. So there are a few things I want to point out, and then I will stop and And I'm very happy to have a discussion about these things. So anything that, any interaction you may have between quantum objects, according to this view, has got to be ultimately quantum mechanical. So if your particle can exist in all of these directions at the same time, each of them, and if these two particles, imagine they're two electrons, they're coupled electrostatically as well. They repel each other. Now, what quantum mechanics says to us, and this was an argument that Heisenberg used at the very beginning, is that whatever force is acting between the two must act between all positions simultaneously. So quantum superposition is a bit like a virus. As soon as it gets in touch with anything, this other thing has got to become quantum mechanical automatically. Otherwise, you cannot explain anything within quantum mechanics. So it's not just that you have a force between this position and that position, it's all of them coupled and interacting in quantum mechanics simultaneously. And now the interesting thing is this. We know that this is true in electromagnetism, but we don't know if this is true with gravity. Gravity is our outstanding, so to speak, force. Some people would even argue whether it's a force. But it's an outstanding force if you look at it together with other forces that have been quantized. It's outstanding in the sense that we still think of it classically. And the question is, can we get an idea how to test this kind of stuff? And this is basically a paper that I wrote with Chiara Maletto and another group, Sugato, Bose, and others have written, which is a test. I want to show it to you because I think it's so simple to understand that you can present it really at any level. There's no mathematics needed at all. It entails a mass that you put in a superposition, and we know how to do this with relatively massive objects. So you can take a very complex molecule and you can really beam split it, so to speak. You can send this molecule in two different directions simultaneously, a bit like with an alpha particle. It's just alpha particle is too small to be a good test for gravity because gravity is a weak force. And you have another mass of the same kind. And the question you're asking is, does gravity really couple all of these positions of the mass simultaneously? That's the interesting question here. Is it going to act just when the particle is here and here, or is it going to act between all of these possible locations of both of the particles simultaneously? And that's where the bets are. There are many people who are now interested in this experiment. It's an experiment that's accessible with the current technology. I'm aware of at least 3 or 4 groups now racing towards this. And it would be amazing because if the two particles really manage to get entangled, always it's Schrodinger's entanglement that's the signature feature of all of these things. If they manage to get entangled through gravity, this would be for us a conclusion that gravity does act in a quantum mechanical way as well. And this would be amazing. Once, when I talked about this once, a colleague of mine approached me from Imperial and said to me, it would be the first falsification of general relativity. And it's true, because general relativity is a fully classical theory, like I said. The entities there are just numbers. They're complex numbers. There are many of them. They're complicated in a way. However, they are basically just real numbers, like in Newtonian physics. And this one would say, in order to explain this kind of entanglement, you need Q numbers. It would just prove that even gravity requires this kind of quantum information. We don't know, of course, what the outcome is. In a way, as you might guess, of course, I'm betting on these two masses coming out entangled through gravity. But the interesting thing, speaking in terms of Shannon information now, would be if this didn't happen. That would really tell us something surprising, that gravity may not be quantum after all. So I think that would be a bigger surprise to to most of my, my colleagues. There are many systems that are proposed to do this. The technology I have in mind is maybe slightly different to this one. But this is the coverage. I think this was sometime in a couple of years ago in the Scientific American. And basically the idea is to take two nanospheres. So these are the objects that are basically a nanogram inside, 10 to minus 12 kilograms, if you like. So 1,000 billion times smaller than a kilogram. It's still a very large object for atomic physics. It's something that's not easy to put in a superposition of being in two places at the same time. But one possibility is simply to take two such oscillators, put them very close to one another so they have a strong gravitational interaction, put each of them in a superposition of being in two places at the same time, and then observing whether the two nanospheres become entangled, quantum entangled. And there are many tests for that. So the bottom line is really that we have this frontier to explore, where if we go into larger and larger systems, there are many views of physics. Some of them claim that quantum mechanics will fail when it encounters gravity or when it encounters living systems or anything like that. And other views, the ones like the one I'm advocating, are saying, no, it's all okay, actually. It's a consistent theory. Obviously, we don't know if nature is like that. But I think what's exciting to us is really to test this kind of feature. So are different components of the gravitational field, if you like, are they really quantum numbers? And this is one of the experiments that would do that. I don't want to take you through all of these details, but there is one thing that I really want to emphasize again, because I think it's interesting and it's maybe something you wouldn't have heard before. Entanglement is not spooky action at the distance, as Einstein claimed. It doesn't allow any spooky action at the distance. In fact, quite the opposite. It's there to preserve locality. If you see, it's because of entanglement that things cannot happen faster than the speed of light. That's the beauty of quantum mechanics. So once you swallowed the quantum numbers, the quantum interpretation, that the underlying elements of reality are these weird tables of information, if you like, quantum information. The rest follows. You don't have to worry about anything else. All of the properties that we like from classical physics are automatically absorbed by this. So this could be a bad news for some people who thought that maybe instantaneously we can travel from here to Mars or any other places. Quantum mechanics, unfortunately, does not allow anything like that. So in that sense is similar, if you like, to classical physics. So the last thing I really want to talk about is that similar experiments, and I think this goes in the direction of Schrodinger's cat experiment. So I said that what kind of view of quantum mechanics you have influences what kind of experiments you'd be planning and what kind of features you'd be testing. You can test gravity, whether it's quantum mechanical, but you can also test to what degree living systems are quantum mechanical. Are they really also described by these Q numbers? Can they also be entangled to other objects that we already know are quantum mechanical? And this also is a big debate. There are certainly some of my colleagues who believe that quantum mechanics collapses when it encounters living systems. Sometimes they make it even more complex. They say, oh, maybe a living system with consciousness could collapse this. Sometimes consciousness is credited for collapsing quantum mechanics. And I'm against all of this. I'm actually betting that it's going to conform to exactly this kind of Q reality. And I think that's what's interesting for us to test. So this was one of the sets of experiments that we did. This was Dave Coles, a colleague of mine at that time, who took a single bacterium, living bacterium, and coupled it to light inside a microcavity. So these are two mirrors that are extremely millimeters away from one another. and they're there to bounce the light inside this cavity and make sure that it stays long enough that it can really couple to this biological system. So we really are trying to go in the direction of Schrodinger's cat. Can you really take a living system and keep it in a superposition? And is there any problem with that, actually? I think initially Schrodinger thought this was problematic. And he almost offered his cat paper as a paradox. Said, how can this be? Look, if you extrapolate this to the macroscopic domain, you've got dead and alive cats. But actually 20 years down the line, he changes his mind. He says, yeah, that's the only way this can be. And I'm kind of in that branch of research. It's the only way it can be, as far as we understand now. We may be surprised by these kind of experiments, but so far there are no surprises. So basically what Dave did is looked at some of these internal energy levels of this bacterium. And what he could, I don't want to bore you too much, but what he could detect is that there is a change inside the energy structure that when two of these levels should actually become the same, they should assume the same energy, if you like, because they become entangled to the light in the cavity, you see a gap between them. So that was a very simple witness for us that all he needed to do is shine some light onto this sample and see whether there was light that corresponds exactly to the frequency that matches this energy difference. So if you look at the energy levels of the bacterium outside of this cavity, they're very different, if you like, to inside the cavity, and that's because the bacterium becomes entangled to the light inside the cavity. So clearly we know that there is no problem with being alive and being entangled at the same time. It doesn't collapse these superpositions. In fact, it just joins them and exists simultaneously in this way. And that's what's interesting. And actually, is another experiment where another colleague of mine, Rainer Dunke in Singapore, took a tardigrade. He took a tardigrade because these are very robust biological entities. They can survive very low temperatures, low pressures. And his quantum bits, superconducting bits, needed to be cooled down to a very low temperature. So basically, he was thinking, what animal can I put there that would still survive 4 degrees of Kelvin? Okay, so 100 times lower than the room temperature here. And he thought tardigrades, you know, they really have this reputation that they can survive almost anything. And actually, he coupled this tardigrade to a superconducting bit. There were 2 qubits, which you can prove are entangled experimentally. He did exactly the set of experiments that led to the Nobel Prizes a couple of years ago. He did them on superconducting qubits, but one of them had a living system, had a tardigrade coupled to it. And so this is really interesting. So it shows you that actually, at least at this level of our understanding, it's perfectly okay to treat living systems in a fully quantum mechanical way. There isn't going to be any contradiction. They really can, at some scale, exist in a superposition as well. And this is really mind-blowing. Like I said, it's kind of going towards Schrodinger's cat. There were some movies, I think, that I can't show you here. They're not recorded here, but he was even recording how tardigrades behave there and so on. And they're very boring creatures. They don't do much. They're very slow. So ultimately, what we'd really like to do, and I think I'm gonna conclude with a more philosophical bit in the last 10 minutes. But I want to show you that what we are going towards, and this is currently funded by the Moore Foundation. All of my projects are funded by this kind of adventurous foundations. No government would want to do anything like this. It's too adventurous. I think they're too incremental. Anyway, don't get me started on this topic of funding. But what we have, they've given us about $3 million over 5 years to entangle 2 living bacteria. So not just one bacterium entangled to light, but why can't you take 2 of them? And indeed, why can't you do that? It's a challenging, experimentally challenging issue. However, you know, if you follow this logic, nothing should go wrong with this kind of thing. So what we have in mind, very crudely speaking, is one living system in one optical cavity, macroscopically half a meter away, separated from another living system in another cavity. So these are tiny, tiny things, and they're sitting inside cryogenics. These are very expensive fridges. Like I said, they get you down to 4 Kelvin or even lower than that, liquid helium. And what you want to do is send a simple quantum system, like a photon, a particle of light. You want to split it so that it goes 2 ways simultaneously, and now it gets absorbed by this bacterium and not by that bacterium, and vice versa. And that sounds really interesting. So now you've got 2 living systems, one of which is excited and the other one is not, plus, so to speak, quantum mechanically at the same time, vice versa. And that's really interesting. Now, yes, it's not as impressive as Schrodinger's cat, simply because cats are much more complicated. But even a cat, so the problem, that's the bit I want to close with. The problem with all of these discussions is that we really don't have a good way of asking this system, how do you feel? What does it mean to be in a superposition of this kind? And the analysis I was showing you before by Heisenberg and Darwin and Mott and Schrodinger, Everett, would say nothing extraordinary, nothing unusual from what you are used to now. It's just what it means is that you really exist in multiple quantum realities simultaneously. But again, the reason why this experiment, yes, it's beautiful, yes, it's challenging, it's going to get probably cover Nature magazine story if it happens, but it's not going to be wow in the sense of, what if we did with a more complex system? Can we do this with a conscious system? Can we do this with something that we can communicate with? Put them in a superposition and ask them, what do you feel now? Are you in 2 minds or what's going on? So I don't have an answer to that, but I'll show you a thought experiment by my colleague David Deutsch, actually at Oxford, invented quantum computers. And there is a reason for that, like I said. He invented them precisely because he thought about reality in these multiple ways that take place simultaneously. So Schrodinger's cat. What I want to tell you very briefly, again, forget about the fact that this is an extremely challenging experiment. I want to take you through some interesting steps. It's still a thought experiment. God knows if we're ever going to be able to operate with complex systems. So instead of a cat, actually, think about a human being inside. So I like to think of Alice and Bob. There is a quantum particle that exists in 2 places at the same time. And Schrodinger said, in one place, the particle is going to break a bottle with poison, the cat dies. In the other branch, there is no poison, the cat is alive. And his question was, is this how it is? Are both of these branches real? Do they exist simultaneously? And I want to show you a test of that. This is not a philosophical question. It's actually an experimental question. But like I said, you can't talk with cats. So to imagine this, I have to tell you about 2 conscious, okay, maybe some of us can talk with cats, I don't know. It's easier with cats than bacteria. But I think, of course, what you want is another human being there, or artificial intelligence. If any of these people working on artificial intelligence hurry up, and they really could reproduce, I'm very skeptical at the moment about what they're doing, but that's a different topic. But if they could, you might be able to get away with a 1,000 qubit quantum computer inside instead of a living being. And then it becomes a real experiment. Actually, we can do these things. But can a 1,000 qubit quantum computer be conscious? Who knows? So I'm saying, you know, it looks super unrealistic what I'm going to tell you now. However, you may be surprised 5 years down the line. So Alice has Bob there, who observes a quantum object. Forget about the cat even for the moment. In one branch, Bob sees the particle being in one place. In the other branch, Here he is sad because the cat is dead, okay? And here the cat is alive. These are snow cats that my students make when I send them to a conference, okay? They're having fun in France, I think. So Bob looks at a quantum object, and according to Schrödinger, in one branch, he sees the particle in one position, in the other one, in another position. And Schrödinger says that's all okay, it's consistent. How do we know it's okay? That's the question. That's what David asked. And David says, why don't you think about another person outside of the lab, Alice. Alice runs the experiment, actually. She puts the particle in a superposition. She asks Bob to go inside, look at the particle. And now what she says to Bob is she gives him a piece of paper which says, do you see a definitive state? Here I said the definitive state of the cat, but like I said, doesn't have to be a cat. It could be a single atom that's in two different places at the same time. And the interesting thing is that in both branches, if they existed simultaneously, Bob would say yes. In one branch, Bob would say, yes, I see an alive cat, if you want to follow that thought experiment. In the other one, I see a dead cat. But both of them agree that there is a definitive state of affairs here. So you see, quantum mechanics doesn't predict that you would have a fuzzy vision of reality. No, it says exactly that you're going to see the usual classical reality in each of these branches. But now the punchline is that the branches exist simultaneously. And how do we know that? And the question, how do we know that, is exactly how we know that anything exists in a superposition. Every quantum experiment is there to test if things are in two or more states at the same time. So here you would do the same thing. You would basically bring it all back, and that's where the technological challenge is. If you really split a complex system and you want to undo the operation that you did, this is very simple with simple systems, with simple atoms and molecules. With photons, we've done it many times. But with more and more complex systems, this is exceedingly difficult. Because you have to keep track, you have to make sure that it doesn't get entangled to anything else. It has to be sufficiently isolated from the right degrees of freedom, if you like, in order for this to work. So it's an exceedingly complex experiment. But what Alice would then ultimately be able to tell by reversing the whole thing is that Bob, halfway through the experiment, was in he was really in two branches at the same time. So remember, because this entails reversal of the whole experiment, the difficulty is that Alice would have to be able to undo Bob's observation. And that's why I'm trying to say that maybe we could do this with simpler systems. It's very difficult to see how one could undo a human observation because it's a very complex phenomenon. So at the end of this experiment, Bob would come out of the lab not having a clue what just happened. Alice literally erased all of his memory. He would come out, Alice would say, that was a nice experiment. Bob would say, what experiment? What do you mean? I have no idea what's going on. And Alice would say, listen, halfway through the experiment, I asked you if you saw a definitive state of affairs inside. Was the cat alive or dead? Did you see it definitively? And here is your answer. Yes, I see a definitive state of affairs. So the fact that you can put something in a superposition, bring it back deterministically, and yet you have a record that all the observations were just as you would expect them classically, is your proof that these things existed simultaneously. It's mind-blowing to me. It really is even if we are very far from testing something like this, it's a mind-blowing picture of reality. And here I'm saying on this slide, Alice can even tell Bob, I know that you see a definitive outcome. However, I also know, because I'm outside of the whole box, that you are in a superposition across two different branches. So that's very interesting. And the Bob in the other branch can affect Bob in the first branch exactly through what Alice does. Okay, that's another interesting feature of quantum mechanics. The outcomes you don't observe in this universe can affect you in the future because they can come as interferences from other quantum branches. It all sounds like science fiction, but that's what quantum mechanics tells us. And actually, maybe the last thing I want to say, if you're speaking just at the level of quantum logic, quantum bits, the whole thing can be captured and can be done as a proof of principle with just 3 quantum bits. You only need 3 qubits. Anyone these days has 3 qubits of different kinds, photons, superconducting, atomic. And you can really go, a sequence of very simple gates will execute for you the experiment that I described. Now, of course, you're not going to be as impressed because none of these qubits are conscious, like I said. The fun thing would really be to do it with a conscious entity that can respond to you and say, this is what I see, this is how I feel. And quantum mechanics would say they will not report anything unusual. That's the interesting bit. So this is sometimes the view of reality that's called Wigner's friend, in the sense that now you can say, wait a second, what happens if Alice finds out about Bob's outcome, and then she tells it to her friend? And this is exactly the picture, if you extrapolate Schrödinger's cat, that's exactly the complex network of entanglements that you get as the underlying structure of our universe. So literally every time you communicate, every time you interact with another physical system, you are imparting exactly the same quantum nature on this. And it's fully consistent. That's what's interesting. It is a mind-blowing picture of reality, but it is fully consistent. No matter what you read anywhere where people say quantum mechanics is wrong, it can't be right, and so on, it can be right. Logically, there's nothing wrong. Of course, it can fail experimentally, and that's going to give us a lot of food for thought. So the conclusions is simply what I said now. The bit that I like and that I like to emphasize is that in this picture, there isn't a distinction between an observer and the observed system that they're observing. So you could equally, when Bob observes an atom or a photon, you could equally well, in terms of Shannon information as well, state that this atom observes Bob. It's exactly the same amount of entanglement between 2 of them. You don't need observers in quantum mechanics. Actually, you don't need observers in any area of physics. We just like to use observers to illustrate things and to bring them closer to how they are done. But the notion of an observer is not really required. You know, John Bell wrote a lot about it, the Bell's inequalities person. He thought very deeply about this. And he also found the notion of having to introduce an observer into quantum mechanics a bit paradoxical, a bit illogical. So he was joking. Usually he would say, does the person who collapses the quantum mechanical wave function need a bachelor in physics or a PhD? Or, you know, how highly qualified do they need to be? And actually, this tells you that they don't need to be qualified at all. All of this is perfectly consistent between the simplest of objects, starting with simplest and going to the most complex ones. That's the interesting thing about it. And what I'm most excited about, and this is my prediction. Of course, people keep making predictions, and we all do, and we are all proven wrong frequently. But I think by the end of this decade, we're going to have some new physics. The least will be this falsification of general relativity and the realization that gravity itself ought to be quantum, at least at some level. And this is hugely exciting for us physicists. The technology has managed to reach this level. For 100 years, we've had these 2 theories, and we're all probably pretty bored with all of this. We'd like some novelty. And I'm really predicting that by the end of the decade, we will have these experiments, and they'll be informing us what to do there. You might get a new theory, maybe quantum gravity, maybe going beyond that, maybe telling us nature is even weirder than all this. It's all possible. Thank you very much for your attention.